Yuzhe is a PhD candidate at MIT. His research interests include both machine learning and AI for human diseases, health, and medicine. And he's done some very exciting work that has been published in Nature Med, Science Translational Medicine, Europe's ICML, all the premier machine learning conferences, and also featured in media outlets like the Wall Street Journal, Forbes, BBC. He's a recipient of Rising Stars in Data Science and has PhD fellowships from MathWorks and TechData. His work has been deployed in hospitals, including MGH and Mayo Clinic, and in patients' homes for passive health monitoring. His work has also been adopted for clinical trials for drug and biomarker discovery for different diseases, and we are very excited to hear about his research.
Thanks for a very kind introduction, and thanks everyone for being here. So I'm really excited to be here to tell my work today about learning to assess disease and health in your home. So this doesn't work. Let me try. Yeah, no, the clicker doesn't. Yeah, no worries. Yeah, I can stay here. So let me start with someone very special to me, my grandma, and she's 8 years old now, and she's battling with several chronic conditions, hypertension, diabetes, and she's also showing early signs of tremors and memory issues. And whenever her health issues show up, we rush her to the hospital. And there, she receives cares from clinicians and has access to specialized medical diagnosis and treatment tools. So despite these advancements in medical technology and care, my family and my grandma still have several persistent concerns. So she's always been concerned about catching her chronic conditions early. There'll be a way to spot those issues before they get serious. And moreover, with her limited mobility and living far from the nearest medical centers, we always wonder, could she do those medical checkups simply in the home without traveling to the medical centers? And finally, whenever she's up for treatment, especially recently with machine learning and AI increasingly the mix, we wonder whether these modern solutions really work for people like her and tailored to her age, health background, medical history, or even lifestyle. So these questions not only highlight the immediate needs of my family and my grandma, but also resonate with the broader vision for the future of healthcare and disease management. And I believe these are not just concerns from my family and my grandma, and they're widespread problems that we have been facing for decades. And first, clinical visits scheduled by people are very occasional, and the intervals between two visits are over several months or even years. And that's a problem because it means diagnosis can be significantly delayed. And a lot of times, we don't catch diseases until they reach advanced stages. And this is even exacerbated by the huge dark spaces in healthcare that are never observed by any clinicians. So taking cancer as an example, the risk of death increases dramatically if delayed only by 1 month. And this is what creates a time gap. In addition, because of the shortage of clinicians, hospital care was only limited to a small group of patients, and not everyone can easily access healthcare resources. For example, it's pretty shocking that for over 40% of those with Parkinson's never see a specialist due to healthcare inequities, such as limited access to specialized medical centers. And this causes the gap in location. And further, with the rise of AI for simple tasks like triage or screening, it's crucial that these technologies work for every single patient it serves. But often, this AI model could fail in unexpected ways, like in new environments or patient subpopulations. For example, healthcare company Epic uses machine learning to generate early warnings for those with sepsis. So Epic trained a model, ensured that it worked, and then deployed it to hundreds of other hospitals. However, in those new settings, the model frequently misdiagnoses patients. And this raises the individual gap, where the solution isn't just about disease, but about the person it is affecting. So how should we bridge these gaps? And let's envision a future. Let's imagine powerful AI models that can see into the future and detect chronic conditions even before they show clinical signs. And what if we can simply do this diagnosis and monitoring simply in our home setting every day without traveling to the clinic? And these new capabilities, grounded by actionable and reliable machine learning systems that enable real-world deployment for each individual in the wild. So I want to tell you about my work today on addressing all these challenges with machine learning, from building early detection biomarker for chronic diseases to in-home sensing of human health remotely, as well as their underlying reliable AI methods to achieve real-world deployment. And here's the outline. I'll start with an AI-based biomarker aimed at early diagnosis of Parkinson's disease. And within this application, we aim to collect data, test, and deploy our system nationally and even internationally. But this is fundamentally challenging because the data from different institutions could be drastically different and highly imbalanced. So I will also dive into how we develop robust machine learning algorithms to basically overcome these challenges and to make the model really deployable and tested on thousands of individuals. And next, we'll move from the medical discovery for disease detection to the actual delivery of medical care right into a patient's home. So sensing vitals, such as your breathing and heart rate, has been shown possible to just use an off-the-shelf camera from a smartphone. But they're not scalable because the high-quality labels of these vitals are extremely limited. So I'll also tell you how we address this label scarcity challenge to make this camera-based vital sensing mechanism or systems really work and deployable in the realistic settings. All right, so that's the overview. And each project here focuses on addressing a core challenge in today's medicine, from medical discovery in disease biomarkers to medical delivery from clinics to patients' homes. And both of these novel healthcare capabilities are achieved by designing new machine learning algorithms to address these realistic medical data problems. Okay, so let's dive in. And I'll start with our paper published in Nature Medicine for early diagnosis of Parkinson's disease using our daily nocturnal breathing signal. And together, I'll also introduce the core machine learning algorithms we proposed to address this domain gap and data imbalance issue, which are also broadly applicable to other high-stakes applications. And again, I'm very fortunate to collaborate with many hospitals and clinicians to really test and deploy our system in real setups. So we all know Michael J. Fox, one of the most well-known TV show and movie star, with his famous Back to the Future series. And here is an interview video by Michael. So from the video, you can clearly observe his irregular body movements and his hand tremors. And in fact, this is because Michael was diagnosed with Parkinson's disease, or PD in short. So what is PD? PD is the fastest growing neurological disease in the world. Over 1 million people in the States and 10 million people worldwide are living with PD as of 2020, which results in an economic burden of $52 billion per year. However, a key difficulty in Parkinson's is that we cannot diagnose it in time. And in clinics, the disease is typically diagnosed based on motor symptoms, such as tremor and rigidity. However, these motor symptoms often show up many years after the onset of the disease. And by the time when clinical diagnosis is made, the disease has already been progressed for tens of years, causing non-reversible damage to the brain. So the challenge here isn't just to identify Parkinson's once it's visibly affecting someone, like the picture on the right. So the real goal is to have the foresight to catch the disease early on, even before someone has any clinical signs. And people have thought about how to get this foresight for decades. And over the years, researchers have studied CSF, neuroimaging test, and even blood chemical evaluation as potential early diagnosis biomarker. And while these markers have shown pretty good diagnostic accuracy, they come with significant drawbacks. They're invasive, expensive, and require access to specialized medical centers. And as a result, they can hardly diagnose disease in an early stage. So we ask ourselves, could we find a marker that is both accessible for regular home usage while being as accurate as these clinical-based methods? So the answer is yes. And we have developed an AI-based system that analyzes our nocturnal breathing signals to diagnose Parkinson's multiple years before the clinics. So the immediate question is, why focusing on breathing? So the connection between Parkinson's and breathing was noted as early as 1817 in the first work by Dr. James Parkinson. And over the years, clinically, it is shown that early-stage Parkinson's can have symptoms in their brainstem areas that control our breathing, which can be reflected later in the sleep breathing disorder and the weakness of their respiratory muscle functions. And more importantly, monitoring breathing is simple, it is non-obtrusive, low cost, and it can be done every day in the home setting. So here's how our system works. We basically capture the breathing data either from a breathing belt or by the subject, or uses a wireless device that transmits wireless signal and analyze the reflection to extract the breathing signal. And with either method, we're able to extract a full night of nocturnal breathing data. And after capturing this nocturnal breathing, we then design an AI model to directly learn and extract the disease information from the data. The model has two outputs, whether the person has PD or not. And if they do have PD, assess their severity of the disease in accordance with the gold standard clinical measure. And now, before diving into the technical details, let me give you a preview of our results and their significance. So on the left, you'll see the diverse data sets we used to evaluate our system. So we basically collaborate with many institutions nationally to ensure that our method, our system actually work. And despite these data set differences across multiple centers, we show actually very consistent and robust diagnosis accuracy. And on the right, we leverage retrospective data, which includes multiple visits from the same set of subjects. And it allows us to test for subjects who are only diagnosed clinically for Parkinson's years later. So remarkably, our model is able to diagnose these patients who have visits with like intervals of 6 years, basically early on in their disease stage, which is like 6 years earlier compared to the clinicians. So the question is, how did we do it? So recall that we want a model that takes in the full night nocturnal breathing signal and output whether the person has PD or not, and also assess their disease severity score. So let's focus on the binary classification first. So to construct our model, why not begin with some classic methods, let's say a support vector machine. And here are the results. So on our test set, the SVM achieves an AUC, which is our accuracy measure, of just around 0.5. And that's essentially random guess. So clearly we need to go deeper. So what if we turn to the latest in deep learning, let's say transformer models, Like, could these state-of-the-art approaches be the answer? Oh, go ahead. Sure, yeah.
You're looking for a disease that's more than one night, and so what type of data are you, like how many nights, how many, you know?
Sure, yeah. The question is about whether, because we have like multiple nights, like what is the input unit for the model? So it's just like one night, just need one night of breathing data. So yeah, so like going back, yeah, feel free to ask questions and feel free to interrupt. So basically we asked like whether this state-of-the-art models in deep learning could be the answer. But unfortunately, even with these advanced methods, they perform just marginally better than random guess. So what's the blocker here? And in fact, we identified two key challenges we need to address for this modeling. And first, the input nocturnal breathing signals for one night is high dimensional with tens of hours. And whereas the output about disease is extremely sparse. So we're essentially trying to infer one bit of information from a very high dimensional and dense input. And this will result in a problem called overfitting in machine learning, where the model might find spurious correlation of features in the very dense input while learning nothing related to the disease itself. And additionally, because our data comes from multiple sources, and each with its unique measurement setup, causing the domain gaps between different institutions. And if you take a closer look, we can see there exists significant data imbalance within each institution, as well as the divergence of such imbalance across different domains. And therefore, we are facing the complex issue of multi-domain data imbalance. So for the first question, like how should we ensure our model training is properly regulated to extract useful information about the disease itself? So our solution is inspired by the link between Parkinson's and our brain activity. Also, you know, Parkinson's is a neurodegenerative disease. And in fact, when we go to sleep, our brain activity fluctuates throughout the night, which can be quantified by our brain EEG signals. And based on different frequencies of our brain waves, we can divide the EEG signals into 4 different EEG frequency bands, from low to high frequencies. And these different EEG activities are associated with different physiological functions of our brain, which naturally provide useful information for modeling neurodegenerative diseases. And you might wonder, because our input is the breathing signals, can we actually predict this EEG information just from our breathing? So the answer is yes. And we show that just by using our nocturnal breathing signals, we can reconstruct this full night EEG activity with a high accuracy. And such a prediction task could bring natural dense supervision for our model. So specifically, instead of directly predicting disease information, we propose to add another prediction branch to reconstruct our EEG activity from our breathing data. And this essentially forms a multitask learning framework where this EEG prediction serves as an auxiliary task to regularize the model training to learn useful information for the disease. And indeed, by integrating this auxiliary task, we see a significant performance increase from chance level to impressive 80% accuracy. But there's still another issue. And we noticed that the performance within across different domains were not balanced. And this discrepancy largely comes from the fact that we're using multiple sources and each with its unique data imbalance within the institution. So let's consider a scenario where we have data from 3 different sites. And because of data imbalance, the model may not learn equally well from all the samples, especially for the minority ones. And moreover, because the breathing data could also differ from different sites based on the environment, based on the population, or even based on the measurement device itself. And such domain gaps could lead the network to rely on shortcuts in classification. Go ahead.
Clarification similar to what you were asking, is the gap between when the diagnosis was done and when the data, the features were collected different across different sites as well? And what is the ballpark number?
Oh yeah, that's a good point. So because the disease is actually non-reversible, so once it's diagnosed, it is diagnosed.
Yeah.
So regarding your question, I think like for most data sets, we don't match the exact diagnosis because diagnosis can be delayed.
Yeah.
So we just associate whether they're diagnosed by the gold standard clinical metric with their data after the diagnosis. Yeah.
Okay.
But we do have the time after diagnosis, but we don't use that in our model.
No, I'm asking before the diagnosis, like how soon was the data collected? What's the gap between when the data was collected and the time of diagnosis?
I see. So for all the
And is that different across different sites?
yeah, that's a good question. I should check. But so basically there are two types of data. Like one type is we do have data before their clinical diagnosis, and that was used for later experiments and not used in this one.
Okay.
This one is just simply for modeling, like whether we
Okay.
can diagnose it. Go ahead.
Go back one slide.
Sure, yeah. You mean
Or
this
one
one?
more.
Okay.
So just a quick question here. So like end-to-end prediction versus some intermediary prediction.
Sure.
Very significant improvement. Could you just like maybe speak a little bit about like what were some of the experimental controls you created to try and understand why we saw such a drastic change when you went from end-to-end prediction versus intermediary prediction?
When you say intermediate, you mean like using this
You
modality?
generated the EEG
first.
activity, and then when you generate the EEG activity and then do this analysis, you get much better performance. So, how did you make sure the model wasn't cheating or there wasn't something else going on when you went from 0.55 to 0.81?
Got you.
Invested?
Yeah. That's a good point. So basically for this AUC, when we say the test set is always an external test set. So basically we develop our model on some like domains or distributions, and we test it on a like out of distribution or never seen data set. So this ensures that we're actually testing the generalizability, whether the model is actually learning this information. And yeah, so basically we found this task to be viable, like as you said, like no matter whether you use like which backbone of the model will not actually improve the performance. So basically the key information here is you need dense supervision in the task basically. And you cannot just rely on one single label to do the classification, using that label as a supervision signal. That is like basically very little information. Yeah.
And then how did you generate the intermediary, the EEG activity?
Sure, yeah. So for some of the data we have, we're leveraging data from the sleep labs. So we basically have the ground truth like electrodes, proton head. So we have the ground truth EEG recording, so that can serve as the supervision. And that's just part of the data. So like once we have that data, we propagate the loss, and we don't have data, then we just train with the single label. Right. Thanks. So yeah, so basically going back to this example, we are saying there's another issue of because we are learning from multiple domains, and each could exhibit their distinct like imbalance type. Let's just consider this example where we have data from 3 sides. Okay, or I talk about this. Okay, so we said like there could be because of data imbalance, there could be this shortcut problem. And for instance, in this setup, it might label all samples from one site as Parkinson's and all other samples as controls. And in this case, the overall accuracy could still be pretty high, like 80%, but very poor performance for the minority group. And ideally, we want balanced accuracies within each domain and each class. And this ensures that the model is actually learning to predict Parkinson's rather than some extraneous factors like the domain itself. So to achieve this, we must align this imbalanced domain, filtering out irrelevant information specific to the measurement setup or condition. And concretely, this forms a multi-domain imbalanced learning problem. And because the breathing is highly dependent on the domain itself, machine learning algorithms don't generalize well in this case. And what we want here is an aligned representations across these imbalanced domains. And therefore, the learning algorithm can generalize better to unseen institutions and new patients. And specifically, to align these distributions, we want to ensure that samples from the same class but different domains are close to each other. While simultaneously, we aim to increase the distance for samples between different classes within the same domain, and also between different classes across different domains. And to quantify this, we can simply define 3 statistics, namely alpha for the same class, different domains, beta for different classes, but same domain, as well as gamma for different classes and different domains. And intuitively, to make sure we align these domains, we will aim for a lower alpha and a larger beta and gamma. So here we use this mu to represent each domain class pair and start with an approach that directly optimizes these alpha, beta, and gamma forms. So intuitively, this domain alignment loss seems promising because the numerator here actually represents the positive cross-domain pairs, which exactly corresponds to alpha. And the denominator here represents the negative cross-class pairs, which corresponds directly to beta and gamma. So by definition, if we optimize this loss, it will align these domains, leading to lower alpha and higher beta and gamma. However, because this loss is actually independent of the number of samples within each domain class pair, it does not address the label imbalance problem. So the loss can be dominated by the majority domain class pair, where there are many samples, and they can skew the model training. So to address this imbalance issue, we introduce this balanced domain alignment loss. And this is achieved by simply substituting the original distance function with what we call a balanced distance. And this simply divides the original distance by the number of samples within each domain class pair. And by doing this, we aim to account for the varying sample sizes within each group and ensuring that each contributes equally to the final loss. So the question now is, does this approach work in practice? So in our paper, we present a theorem which states that this Boda loss is actually a tight upper bound for alpha, beta, and gamma metrics. And just to put it simply, this means that by minimizing this loss, we're directly optimizing this alpha, beta, and gamma metrics in the form we want. And this optimization will translate to improved model performance in this multi-domain data imbalance problem. All right, so let me show you the results. We basically create a very large data set by collaborating with many institutions and leverage both retrospective data and prospective clinical trials. And in total, we have over 7,000 individuals and over 700 PD patients. So with our AI model and these customized algorithms and losses, we were able to achieve this consistent and robust performance across different institutions, as well as across different data collecting devices. So the model also shows initial evidence for diagnosing the patients in an early stage. And in our dataset, we identify a group of patients who were only diagnosed 6 years later in the clinic, but they were not diagnosed 6 years before. And we do have data from all these 2 visits. So we directly test our model on this early cross data to test whether it can diagnose these patients in an earlier stage. And first, we collect age and gender and other comorbidity matched control subjects, also from the same study in the early cross, and show that our model can successfully diagnose them as normal controls. And further, when we tested on this prodromal PD group, it shows pretty good diagnostic accuracies, and it shows the ability to catch these foresights to diagnose them in an early stage. And I want to mention that this is an early result because as you can read from the numbers, sample size here, it is pretty limited. And because of the inherent limitation in the dataset construction process. But this result is actually very interesting and promising that such an AI-driven approach is able to objectively diagnose patients in much earlier stage.
Sorry, maybe I missed it, but do you have breathing data from the visit one?
Yes, basically this is kind of like a sleep study.
Oh, I
and then
see.
They have like multiple visits.
So you waited 6 years to do that, okay.
Yeah, no, so this is actually from a retrospective, like they already collected.
Oh, I see, okay, got it.
So that's one of the reasons like why we have a very limited size.
Can I follow up on this? Why is there sleep data on the first visit?
Yeah, because
Like, not everybody who goes to see their doctor gets a sleep study. Were they suspected for, or?
yeah, good question. So basically, like for individuals who come to sleep study, they actually have some like inclusion criteria. So they have some sleep disorders or other like, like sleep apnea. But basically, in this study, like they further have some patients who will develop Parkinson's in the later course. So that's why like we can test on the early course.
So is it just that like you looked at everyone who had a sleep study, you confirmed they didn't have Parkinson's, then you look 6 years into the future, you find the ones who have Parkinson's, that's your 12, and then you put the other 476 who had sleep studies and were not diagnosed with Parkinson's.
Exactly, yes.
If you were to predict the PD from the EEG data,
Yeah.
how would be is the performance very good?
Yeah, very good point. So if you just predict it from EEG, you will also get an 80% accuracy. And I think like our advantage is EEG is not that accessible.
Yeah.
Like I cannot do it at home.
Can I ask a question about the data, the way the signal is collected? So you talked about the belt, but you also talked about a wireless signal being collected.
Oh, yeah.
Are those collected together? I imagine the kind of sensor data you're able to get from the belt is different than the wireless signal, but if both are being used here, I was curious.
Yeah, very good point. No. So I mentioned like this part is actually retrospective data, like where they're already collected like multiple years ago. And we also can do some prospective studies, like by collecting the wireless sense. Like imagine if you have a wireless box here, you're actually monitoring the longitudinal data.
That would be like primarily auditory signal for the breathing as opposed to sensor data from like physiological breathing.
Yeah. So basically, so that's in another community, basically in mobile sensor community, already extract very good breathing data, like almost the same as the breathing belt, just using the wireless device. So yeah.
All right, I'm still a little stuck on this. And
sure.
I'll ask one more question, but then move on.
Go ahead.
Have you looked at, is there anything about why they were, why they have, what was the initial reason why they got the sleep study?
Sure, yeah. So there are definitely some inclusion criteria, like they have
Whether those reasons had anything to do with, I'm wondering if there are sleep studies that are done differently based on why people are suggested to do those sleep studies. And then there are some confounders there that you are not accounting for.
Gotcha. Yeah, very good point. So I think so for these studies, they basically aim for like for example, sleep disorders, like REM behavior, like REM sleep disorder, like something. But to just like I think we did the best to match the components. Basically, they're under the same inclusion criteria, and some are not developed Parkinson's. So they're exactly the very good set of controls. They're in the same age, in the same like gender distribution, and all other like sleep problems are matched. It's just like some developed Parkinson's or something.
It'd be interesting to see whether the distribution of the indications that suggested sleep study are the same between the ones that you ended up identifying Parkinson's at and the ones that
that's very good point. Yeah, I think like we didn't cover this part. Like there's like hundreds of variables.
Right, I understand.
Yeah, but that's actually very good point. Cool. So yeah. So going back, basically, if you recall, like our system is also able to predict the disease severity. So basically correlate our prediction with the gold standard to show actually our prediction of the severity is also statistically significant and well correlated with gold standard. And here comes the exciting part. Because we can evaluate the breathing every day at home, and once we can track the severity, we can monitor the progression of the disease in a much fine-grained manner. So let me show you one individual we monitored using like the wireless device for more than 1 year. So first, let's see this traditional clinical measure of PD severity. And they're usually done like every 6 months. And they're very infrequent and can exhibit large variances. So you can read from the month 6 score that significantly deviates from the baseline. And that's essentially impossible because we know Parkinson's is a progressive disorder and is non-reversible as of now. And now let's look at the predictions from our model. So because we can evaluate it every day, we can aggregate a much fine-grained results of this progression and disease trajectory over time. And this not only let us understand the disease progression in a much more personalized level, but also have implications for how we can improve the drug clinical trials for these neurological diseases. Okay, so this is the first part on this early diagnosis biomarker for Parkinson's disease. Oh, go ahead.
Sorry,
Yeah.
I'm just-
Oh, yeah, go ahead. No.
So for example, type 2 diabetes and Parkinson,
Mhm.
so they share genetic architecture, meaning that there's a shared genetic risk. And sometimes you get a sleep study because if you have type 2 diabetes, you might be overweight, and then because of they send you to sleep study. So I'm wondering if you're already selecting for people that have genetic risk for Parkinson already because they might have type 2 diabetes.
Yeah, that's a good point. So I think like in our so that's not something we can control because that's the retrospective study. But we do have like our own collected data, like on a much diverse population with wireless sensors. So basically, our models also have like very high like diagnostic accuracies on those like wider populations. So I believe that we are actually catching signals about disease, but we are not doing it perfectly. So it definitely means there could be some like confounding factors here. But that I believe will include more modalities into the study, which is also in my future.
Thank you.
Yeah, go ahead.
I have a question about the data imbalance, and I know you have the whole second part to your talk.
No worries, no worries.
So that data imbalance scenario, I assume happens a lot like different in research studies, maybe in real world. How have you tested other baseline algorithms, or have you tested your own method on other data imbalance scenarios?
For sure, yeah. So this loss is actually, sorry, not this loss. Yeah. So basically, this loss is actually tested on like many other tasks, including like computer vision and natural language process. As you can see, like this theme is actually pretty general. Basically, you have data from like multiple institutions, and they could naturally be imbalanced. So we actually have a separate paper on this problem, and basically analyze the performance of this loss on other tasks.
And you're also able to try other methods on your data set.
Exactly, yes. We have like
And to reach how do these help us?
Oh yeah, basically this method would be fast. I think that's the high level takeaway. But I would say like so here are actually like 2 core problems. First one is we have domains. There are some gaps, and we have data imbalance. So I would say like past efforts on this part only consider like data imbalance, like how do you model data imbalance, or how do you merge different domains. But if these 2 factors appear in the same time, there needs some like new machine learning. Great. Thanks for the question. So I will go faster in the second half. Okay, so that's the first part. And in the second half, we will basically delve into challenges of how we can actually deliver care to remote users to monitor their vitals. And because, okay, so yeah, again, like this is a collaboration with many good guys from UW and Google Health. So the background is like this. Basically, sensing human vitals through cameras has shown to be feasible just using an off-the-shelf camera with AI. And imagine being able to extract your heart rate, your respiration, and even sometimes your blood pressure just by looking at your smartphone. And this is really exciting, as more than 7 billion people on Earth hold a smartphone. And if you can deploy this capability in the wild, it would be universally accessible and enable in-home measurement or checkup of your vitals. But this is still far from being scalable because the labels of these vitals are really limited. So to collect the data, the participant need to attach clinical sensors onto their body to actually measure the synchronized vital signals with their video. And following this, we could collect a well-synchronized label data point with high-quality vital measurements. And then we follow the same procedure to collect more paired data and formulate a static database, and then train your favorite machine learning models to predict these vitals from input video. And we hope to deploy this model to be usable in practice. The question is, does that work? And indeed, if you test them in controlled environments, they already show pretty good performance. And the performance already satisfies the standard in consumer health, consumer wearable technologies. But what if we deploy them in realistic, diverse real-life scenarios? For example, in varying background or lighting conditions, with significant body movements, or on specific demographic population, like darker skinned people. So the performance of state-of-the-art AI models would dramatically decrease. And to address this, ideally, we need to go back to collect high-quality, synchronized labels or data points in those diverse scenarios and retrain our model. But this is really challenging and resource-intensive. But what if we could leverage this unlabeled videos, in this vast amount of unlabeled videos in the wild? And for example, I myself can easily record a video in my room. And although I don't have those clinical sensors to measure my ground truth vitals, if you can effectively leverage these unlabeled videos in the wild, we can potentially scale this application to be more realistic and robust in real-world scenarios. So the question we want to tackle in this part is, can we actually do this physiological sensing without using any labels? So in this work, we basically show that we can develop a self-supervised method to scale this application. And here's an overview of our result. Basically, on the left, we show that our model outperforms state-of-the-art, both supervised and self-supervised method by a notable margin. And on the right, you'll see that by incorporating unlabeled videos into our training process, we can significantly improve the performance in those realistic scenarios to be more robust and equitable. So again, how do we do it? So let's first review how self-supervised learning works. And state-of-the-art methods using unlabeled data by defining positive and negative pairs and do contrasting on top of them to learn useful features from the data itself. So the core idea here is to augment the same sample to create different views of the same sample, and they're treated as positive pairs, and they should be close in the representation space. And the negative pairs here are defined by different samples, and we should simultaneously drive the distance between negative pairs. But how should we do this construction for physiological data? So for example, we want to extract cardiac or breathing estimations from just these video observations. And here we basically magnify the blood volume pulse and the breathing motions across time. So so basically, how should we, what information should we actually extract from this video? So we know that the identity, pose, or the angle of the person are not important. And what are important is the periodic changes of their blood volume pulse and the breathing motions across time. So this tells us that the most important information we should extract is the frequency information from data. And this tells us how we should construct these positive and negative pairs from this video. So we propose frequency domain transformations to construct these negative pairs. And consider an input video which carries an inherent physiological signal. And we then alter the sequence speed or frequency. And this effectively alters the underlying physiological signal. And while the original frequency of the input is unknown, we can effectively create negative views of the same sample. And in addition, we apply transformations that preserve the identity of this video, which means that after the transformation, they have the same frequency or the same physiological signal. And this basically creates the positive and negative pairs for these periodic features. And now another challenge is, once we have this feature extracted and have these positive and negative pairs, how should we measure the similarity between these features to define a loss? And consider this hardware estimation example, and where we denote the extracted periodic features as the anchor. And if we delay the video by a few seconds, we can extract an index shifted version of the feature. And if further reverse the video in the time domain, we can extract an index reversed features. And finally, if we change the speed of the video, we can extract a frequency altered sample. And by definition, we know no matter whether we introduce a small time delay or even reverse the video in the time domain, it does not change the underlying heart rate of this person. So it tells us that a proper periodic feature similarity should induce high similarity for all these features, will capture a gradually change or smoothly change similarity when the frequency varies. So the solution is very straightforward. And traditional similarity measure in machine learning, they use strict index-based index-based differences. Basically, they're doing like index contrast scheme. And when we want to go to the periodic domain, we basically first transform them into the frequency domain. And then we measure the high dimensional distance in the frequency space. And this is what we call a periodic feature similarity, which is designed to enforce this periodic nature of these features. Oh, go ahead.
So all this makes sense. Fourier transforms here, data augmentation with like methods like five cropping and everything like that. But when you also incorporate motion, is there stability in these similarity metrics? Because someone's head is moving and things like that. From frame to frame, the similarity may evaporate. I don't know if you're going to talk about this or not, but I can see how this works when you can heavily control the one dynamic feature that's changing most and create periodicity there. But if someone is moving and things like that, is that hold true or does it fall apart?
Yeah. So basically, the assumption we have is within a short time window, the underlying physiological signal remains the same. So the question is basically, can we actually extract these signals from a large motion? But I think that's just a modeling problem. So basically, we model this by end-to-end model. And yeah, that's still a challenging part. And as you can see, like the performance of current model is like very bad. And we can improve it, but still not perfect. So I think like this is some like actual work to actually model this. Yeah, go ahead.
I'm just saying that we have about 3 minutes left.
Oh, I see. And I actually go very fast. Sorry about that. So basically, yeah, that's all. And we can basically see, we can visually see like how this learns the periodic features. And this is a supervised baseline where we have all the labels to train model, and they're well clustered in the two-dimensional space. And for state-of-the-art self-supervised method, they don't capture this periodic or frequency information, and all points are scattered out. And for our method, we don't use any underlying labels, but we can still learn this periodic information by capturing the frequency in the data. And now with these capabilities, we basically can train these models with like a huge amount of unlabeled videos in the wild. And we both tested in a constrained scenario where we have only labeled samples, where small labeled samples outperform the methods. And by incorporating a large number of unlabeled videos, we can even push the performance further. So one case study I want to highlight is this approach to actually improve the algorithmic fairness across different skin tones. We know this camera-based sensing is very sensitive to skin types because different skin absorb the light differently. And to understand this, basically for the supervised methods, they would have like very poor performance for darker skin people. But for our method, because the method itself, if you recall the algorithm itself, it actually tries to remove extraneous information that is not related to the frequency itself. So actually, we're removing the person's appearance or so on and so forth information, and it can achieve better performance and moving towards a more inclusive and equitable technology. Okay, I'm speaking very fast. And so, okay, I'll just like jump over this part and basically there's some community effort and quickly talk about the future work. So based on so future work, like one very exciting part I want to do in the future is to use machine learning to to understand chronic diseases more deeply and broadly. So if you recall, like we started in the first project, we started with Parkinson's, and we can extract like from sensory data like breathing or EEG, and define our AI model to do diagnosis, severity monitoring, and progression tracking. And I believe this is really a starting point and basis to extend this framework more broadly and deeply. So for example, we really want to understand, in the depth part, we want to understand whether we can do actually patient phenotyping for Parkinson's because it's an umbrella instead of one disease, and also to drug response monitoring, and also try to do intervention based on these insights. And this will require like again like multimodal data, as I just answered like of these questions, and also to design like new learning models to perform over these like complex data sources. Okay, and then we can extend this framework more widely. So we know this can also be applied to similar neurological conditions like Alzheimer's and ALS, and we want to develop a biomarker for objective early diagnosis, objective severity tracking, and even monitoring their medication response. So we have some initiatives, research projects on this front. And also this can even be applied to other chronic diseases like mental health. We know there's no good measures for mental health because they rely on subjective questionnaires. But what if we can develop objective markers to assess their brain state and try to do severity tracking instead of using all these questionnaires, so on and so forth. And I believe these are collaborative efforts and truly looking forward to collaborations. And okay, the final part is another direction I'm excited about is to make models really fair and equitable in the changing world setting. And so this is really not just to make algorithms fair, but really to understand their performance when things change, like under deployment, under shifts, or even under regulation. So as a starting point, we are collaborating like with Marze's group at MIT to try to build benchmarks for evaluating real-world subpopulation shifts, as well as devising like methods to understand the fairness and how to mitigate these biases when models deployed in a completely new environment beyond their training context. Cool. So these are all my collaborators, and looking forward to broader collaborations. And thank you all. I'm happy to take more questions.
In the interest of time, maybe you can take one question from Zoom.
Sure. Yeah.
And folks on Zoom still hear us?
Wait, you can just.
We can still hear you, but I don't have any questions. Well done.
Does anyone have questions? You have 30 seconds to ask questions. Okay, I'm not seeing any questions. So we'll take one question from here, if there are more questions.
Go ahead. Yeah.
Hi, thank you so much for your talk. I guess at the way you kind of framed this was with the importance of home health and like sensing at home as a tool for promoting equity and access to healthcare, which I think is really important and really interesting. But I was wondering what your thoughts are in terms of differing quality of sensors and access to that home healthcare in the first place, because especially in the US, that's something that not everybody has access to.
For sure. Yeah, that's a good question. So I think like our thinking is we first prove that these are easy to track signals. So we first prove that we can actually find some discovery from these signals. And then we try to minimize the capacity to build these systems and then to make it really deployable. So I think we start with some wireless sensors, which are, as you said, like probably more expensive and not that accessible. And we try to, once we know the insight, like we can actually use breathing signals. And then we know like probably just using a smartphone, you can monitor breathing pretty robustly. So I think it's kind of like a process where we need like collaborations between like multiple expertise. We also need hardware people to actually make more accessible hardwares like for sensing, and we need software people to actually do the modeling. So yeah, hopefully this will be the work that scratches the surface, and we try to extend the depth also.